Hi, this is Dr. Soikat Majumdar. Today we will discuss Fermi statistics, its few applications and few numerical problems. It is under the module 5 of statistical mechanics of BSHU PH 101 syllabus. The learning objective is to compute macroscopic properties from the quantum mechanical information about the atoms and molecules of interest. From our previous discussions, today we will find out mean internal energy or average energy of electrons in metal at absolute zero. If any dE, that means n number of electrons within the energy level E and E plus dE, the mean total energy E average, that is the E average of the electrons in metal at absolute zero is, we can represent it like this. E average is equal to, suppose any d number of particles each having energy E. So we are integrating this 0 to Fermi energy. This becomes the total energy, and divided by number of particles is n, so it becomes average energy. Here n represents the total number of electrons in a metal of volume V. We know that from Fermi statistics, any d is equal to GED by 1 plus e to the power EI minus EF by KT, where GED represents number of quantum states within the energy space E and E plus dE. So this 1 by 1 plus e to the power EI minus EF by KT, this means Fe. So we are representing, this one is this up to this part, 1 by this part means Fe. So Fe into GD. So this is Fe. Fe means Fermi distribution. Fermi distribution is 1 by 1 plus e to the power EI minus EF by KT. Thus the average energy E becomes, as per our formula, we are changing this NED as FEG, NED as FEGD, N 1 by N 0 to EF E FEGD. Now from this diagram we know that 0 to EF Fe is equal to 1, and outside this EF to infinity Fe becomes 0. So we can write average energy E is equal to 1 by N integration 0 to EF E, this one is Fe GED plus EF to infinity E Fe GD. So this becomes, this Fe is in this space, Fe is 0, that is from EF to infinity Fe 0, so you are putting here 0, so this integration term becomes 0, and here Fe becomes 1, so integration term becomes EGD. So average energy E is equal to 1 by N integration 0 to EF EGD. Now total number of quantum states in the phase space within the energy range E and E plus D is GED. and already we have derived GED means 8 root 2 pi v by h cube m to the power 3 by 2 e to the power half dE. So putting this value of GED into the average energy expression that we have derived earlier, this is the average energy expression. So putting this value GED here, so we will get 1 by n 0 to epsilon f E. GED means 8 root 2 pi v by h cube m to the power 3 by 2 e to the power half d. So this, all these terms up to this term up to m to the power 3 by 2 is constant. So this will be outside this. So e to the power 1 plus 1 by 2 means 3 by 2. So 8 root 2 pi v by n h cube m to the power 3 by 2 integration 0 to ef e to the power 3 by 2 d. So on integration e to the power 3 by 2, it becomes e to the power 5 by 2 by 5 by 2. So we are writing here as taking this term intact. Now this one becomes 2 by 5 e to the power 5 by 2, and putting the value of the limit, so ef to the power 5 by 2. So this becomes 16 root 2 pi v by nh cube 5. There is another 5 nh cube m to the power 3 by 2 e to the power ef to the power 5 by 2. Now we will put the value of n. Now the total number of electrons is equal to the total number of single particle energy states. We have already calculated. Again I am repeating this part. N is equal to integration 0 to ef NED. So it becomes NED means it is GED, basically e to the power at t is equal to 0, then it becomes Ne becomes GE. Already we have discussed in our earlier lectures. So 1 by h cube, G means 8 root 2 pi v m to the power 3 by 2, and on integration e to the power, this is integration 0 to ef e to the power half d. So n becomes 1 by h cube, that means 8 root 2, here this one becomes 3 by 2, so 2 will be in the numerator part. This one becomes 16 root 2 pi v m to the power 3 by 2, and denominator part 3h cube ef to the power 3 by 2. Now we know the value of n. So we have to put the value of n here. Now what will be the expression of average energy? So average energy E is equal to 1 by n into 3 by 5. This is 3 by 5. Here it is 16 root 2 by 5. We are taking for this term 3. We are just arranging, this one is 3 by 5. So we are multiplying here 3, we are dividing by 3. So this is multiplying, this is dividing. So this 2 will nullify. So but our purpose will be served in this way. 16 root 2 pi v by 3h cube m to the power 3 by 2 ef to the power 3 by 2. It was 5 by 2. We are just arranging like this, 3 by 2 plus 1. So ef to the power 3 by 2 into ef to the power 1. So this becomes ef to the power 5 by 2. Now this part, the cost to arrangement is, we have to find this one is as n. So 16 root 2 pi v by 3h cube m to the power 3 by 2 ef to the power 3 by 2. This is n. So we are putting here n. So 1 by n into 3 by 5 n into ef. So this n and this n will cancel out. So it becomes 3 by 5 ef. So average energy becomes 3 by 5 of Fermi energy. So average energy becomes 3 by 5 EF. This is the expression of mean internal energy E of electrons in metal at absolute zero to its Fermi energy at T is equal to 0 K. Fermi temperature. It is represented as Tf, or in some books it is represented as theta f. Fermi temperature Tf is the ratio of Fermi energy Ef at absolute zero temperature to Boltzmann constant and its corresponding absolute temperature. So Fermi temperature Tf is equal to Ef by K into T. K is the Boltzmann constant. Its value is 1.38 into 10 to the power minus 23 joule per Kelvin. Now let us solve few examples. The question is, calculate the density of states for an electron with energy 5 electron volt constrained to move in a cubical box of length 0.5 millimeter. So supplied data is energy of electron is 5 electron volt and the cubical box, its size is 0.5 millimeter cube, its millimeter 0.5 whole cube millimeter cube. This is the size. Now we have to find out the density of states. We know the density of states of electron is Ge is equal to 8 root 2 pi v by h cube m to the power 3 by 2 e to the power half. So if we know the data of the right hand side, then we can easily find out the density of states. Now what are the values we know? First value is pi. It is known to us, 3.14. V is the volume of the cubical box. Here it is 0.5 millimeter, 0.5 cube into millimeter cube. So millimeter to meter, we have to convert it. So 10 to the power minus 3 whole cube. So this becomes 10 to the power minus 9. 0.5, its cube is 0.125. Now mass of the electron. Mass of the electron is 9.1, 10 to the power minus 31 kg. The value of Planck's constant is 6.6 into 10 to the power minus 34 joule second. And the energy it is already supplied 5 electron volt. So this becomes 5 eV means 5 into 1.6 into 10 to the power minus 19 joule. So it becomes 8 into 10 to the power 9 minus 19 joule. So putting this value, we can easily calculate the energy G, the density of states. G is 1.2 into 10 to the power 37 states per joule. 1.2 10 to the power 37 states per joule, which is the required density of states for the given electron with energy 5 electron volt, and it is constrained to move in a cubical box of length 0.5 millimeter. Next problem is, calculate the probability of finding an electron with energy 6 electron volt in an electron gas at 1000 degrees centigrade if the Fermi energy of the gas is 5 electron volt. So supplied data is energy of the electron, that means 6 electron volt, that means this is EI. Fermi energy is EF, 5 electron volt. So EI minus EF is 1 electron volt. Temperature is 1000 degrees centigrade, that means 1000 plus 273 Kelvin. So probability, its formula is Fe is equal to 1 by e to the power EI minus EF by KT plus 1. So here we know the value is 1 electron volt. 1 electron volt means 1.6 10 to the power minus 19 electron volt, and the value of K is 1.38 10 to the power 23 minus 23 joule per Kelvin. So it becomes temperature, already I have discussed, 1273 Kelvin. So Fe becomes 1 by this 9.6. This becomes 1 electron volt. Here this value, it becomes e to the power 9.11 plus 1. So putting this value, this one becomes 9046.3. 1 by 9046.3. That means 1.105 into 10 to the power minus 4. So this is the Fe. So it's in percentage, if we multiply by 100, it becomes 0.01105 percentage. So this is the required probability in percentage, 0.01105. Come to the next problem. Just there is a twist from the earlier problem. If the probability, that is here the probability is given. If the probability of finding an electron of energy 6 electron volt in an electron gas at 1000 degrees centigrade is 0.01105 percentage. Calculate Fermi energy of the gas. So here this Fe is supplied here. This is this. So Fe is equal to 0.01105 by 100. Energy of the electron is given. Ya is equal to 6 electron volt. That means 6 into 1.6 10 to the power minus 19 joule. That means 9.6 10 to the power minus 19 joule. Value of K is 1.38 10 to the minus 23 joule per Kelvin. Temperature is supplied T, 1000 degrees centigrade. So T is equal to 1000 degrees centigrade means 273 plus 1000 Kelvin. Now putting these values here, Fe means 0.01105 by 100 is equal to 1 by e to the power. We know this one is EI. We do not know EF. We have to find out EF by KT. This is K. This one is T. Which gives, if we calculate, it gives EF is equal to 8 into 10 to the power minus 19 joule. Again, if we divide it by 1.6 into 10 to the power minus 19, so this becomes 5 electron volt. So this is the required Fermi energy of the gas. We can check here the Fermi energy given 5 electron volt and energy of the electron was given 6 electron volt and its temperature was 1000 degrees centigrade. Then the probability was 0.01105. Now the probability is given here. Energy of the electron is also given. Temperature is also given. We have to find out the Fermi energy. So from this problem, Fermi energy was 5 electron volt. So after calculation, this should be also 5 electron volt. Here it is 5 electron volt. Now let us take another example. Calculate the Fermi energy for metallic silver, assuming each atom of silver contains a single free electron. Given density of silver 10.5 gram per cc. Atomic weight of silver is 108. Now, number of density of free electrons is given by n is equal to n with the Avogadro number and v with the n by v. So this is volume. So we can write 6.023 in 10 to the power 3 per unit per molar mass 108 into its density is given 10.5 per cc. So it becomes, after calculation converting it per meter cube, this becomes 5.9 10 to the power 28 per meter cube. This is the n. Now we know the Fermi energy is given by EF is equal to h square by 8m 3 by pi capital N by V to the power 2 by 3. We are representing capital N by V as small n, and the value of small n is 5.9 10 to the power 28. This is the value. So if we put these values 6.6 10 to the power minus 34 whole square by 8 into mass of the electron is 9.1 10 to the power minus 31, pi its value is 3.14, 3 into n means this 5.9 10 to the power 28 to the power 2 by 3 joule. So it becomes 8.8 10 to the power minus 19 joule. Dividing 1.6 into 10 to the minus 19, it becomes 5.5 electron volt. This problem stating if the Fermi energy for metallic silver is 5.5 electron volt, calculate the number of free electrons per unit volume of the metallic silver. Now Fermi energy is supplied. EF is equal to 5.5 electron volt. That means 5.5 1.6 10 to the power minus 19 joule. That becomes 8.8 10 to the power minus 19 joule. Now we have to find out the number of free electrons per unit volume. That means small n. Number of free electrons per unit volume. So we know from this formula h square by 8m 3 by pi capital N by V. Capital N by V means small n. That means small n is equal to n by V. Last PPT we have already written n is equal to capital N by V. That means number of electrons per unit volume. So here we are presenting this one is a small n. So 6.6 10 to the minus 34 whole square by 8 into 9.11 10 to the power minus 31 into 3n by 3.14 to the power 2 by 3. So on solving we will get n is equal to 5.9 into 10 to the power 28 per meter cube. That means number of free electrons per unit volume is 5.9 10 to the power 28, which is the number of free electrons per unit volume in metallic silver. Calculate the total energy of an electron gas at absolute zero temperature for sodium containing 1 free electron per atom. Given density of sodium is 9.7 10 to the power 3 kg per meter cube. Atomic weight of sodium is 23. Now the number of density of the free electrons is small n is equal to capital N by V. Already we know 6.023 10 to the power 23 by its atomic weight is. This is sodium. Its atomic weight should be 23. There is a error. So into its this error, this should be 23 not 108. It is a typographical mistake. So into 9.7 10 to the power 23 per meter cube. So this becomes 2.54 10 to the power 29 per meter cube. Therefore the Fermi energy is given by EF is equal to h square by 8m 3 by pi capital N by V. We are representing it as small n. So this value of small n is this becomes 3 into 2.54 10 to the power 29 by 3.14. So it becomes, on calculation, 23.2 10 to the power minus 19 joule. So Fermi energy becomes 23.2 10 to the power minus 19 joule. Hence, the total energy per unit volume at absolute zero is equal to, this is the total energy per unit volume 1 by V. So we know total energy, average energy is 3 by 5 EF. For n number of electrons, it is n into 3 by 5 EF. Per unit volume means 1 by V. So this one means again small n. So 3 by 5 small n EF. We know the value EF. So you have to put this EF value here, 23.2 10 to the minus 19. And the value of EF is 2.54 10 to the power 29. So calculating this becomes 35.36 10 to the power 10 joule per meter cube. So total energy per unit volume at absolute zero for the sodium containing one free electron per atom is 35.36 10 to the power 10 joule per meter cube.